Good morning and welcome to Rehabilitation Medicine Grand Rounds. And it's my pleasure to welcome an outside speaker today, Dr. Jorge Zuniga from University of Nebraska, Omaha. And Dr. Zuniga is originally from Santiago, Chile, where he received his bachelor's degree, and then went to University of Nebraska to receive a master's and PhD in exercise science at Omaha, and then PhD in Lincoln. And he has quite a varied background in biomechanics, and now is part of the Department of Biomechanics at University of Nebraska, Omaha, where I first met him as part of my role as an external advisor for a Center for Movement Variability. But I found his research quite fascinating. Not only is it technically a very challenging field in developing prosthetic devices for children, but in addition to the research emphasis, he has tried to develop systems that are really have an impact on the lives of children now, because he's developed low-cost approaches and has disseminated the information widely and to various places. He has a current collaboration with some of the physicians at Children's Mercy Hospital here in Kansas City, and so we hope that actually may become part of a team to develop some of these 3D printing approaches to prosthetics in the future. So I don't want to take up any more of Dr. Zuniga's time, because he is I think you'll find this quite fascinating, and because it really does affect the lives of individuals. So welcome, Dr. Zuniga.
Thank you so much. So I have, I think, 45 minutes, so I'm going to time it. Make sure I don't go over. I have a lot of information to give you, so we're going to start this as soon as possible. First of all, I would like to talk a little bit about the place I work, the Biomechanics Research Building. I do have a boss that needs to be happy with me, so that's why I'm talking about this. So basically, the Biomechanics Research Building is a 2-floor building. Is the only standalone biomechanics center that's fully dedicated to research in the United States, and one of the only ones in the world. So the first floor is we have all our laboratories where we do our research, and then the second floor we have the conference rooms, office space, and so on. And the wonderful news I want to share with you is that we're expanding. So we're doubling the size of the center, which is extremely exciting. I cannot express how happy I am about this, because it means more space for research. I see some familiar faces here. Great. So here's a little bit of the layout of the Biomechanics Research Building. We have the administration on top, the researchers, and the research technicians. So the faculty are the ones that do the semi-dirty work in terms of research, and then we have the research assistants, which are the ones that do most of it. This is not a full list, this is just some of them. Next semester we have 2 new faculty coming. So we employ about 70 faculty, staff, and students that work in the center and in the various research projects, and I'm going to mention just a few of them. We do a lot of work with virtual reality. We also do some work with brain imaging. We use FNIRS. Now we got an EEG recently, probably last week. We do a lot of lower limb and upper limb exoskeletons. We do some research with infants, develop, as I said, more sophisticated on soft robotic exoskeleton, and obviously we also do development of prosthetic and assistive devices. Okay, and we are also very encouraged to work with institutions abroad. So I'm showing you here, I have chosen to work with my country. I'm from Chile, so it makes sense. And with the help of the government, we have also being able to develop open few laboratories which are right now implementing the development of 3D printed prosthetics, orthotics for children specifically. So we have had great success with that. Okay, so here's a little bit of an agenda. So when you look at the CDC in terms of impact, it states that about 1,500 children, babies are born with upper limb reductions. And then they also state that 4 of every 10,000 babies are also born with upper limb reductions. The experience that we have had is that this number is probably double that. A lot of the patients we see are actually born somewhere else. So there is a lot of families that adopt children with upper limb, with upper limb reductions, and due to the lack of mandatory registration, they don't appear anywhere. So there is a bunch of children that are in need of some sort of prosthetic or upper limb devices. So some of the difficulties that the CDC has reported is basically related to the motor skills development. Also, some of them, not all, need assistance with daily activities. And also there are some limitations in certain movements, especially those that involve bimanual activities. So, for example, riding a bike, try to play the violin, simple activities such as holding a glass of water and pour water on it. Every activity that's bimanual and that requires stabilization and manipulation are kind of challenging. So the treatment typically are either surgery, rehabilitation, but we have chosen the one that makes the most sense to us, which is the development of prosthetics. So what are the management options? So there's a lot of different views on this, okay? So I'm gonna show you what's out there. So the management options, there are different aspects that are really important on this. One is the timing of the initial prosthetic fitting. Typically, the rule of thumb is the earlier, the better. So how early? It has been reported that typically when a child walks independently, it's better to give him a passive device, and as soon as the child, is between 2 to 4 years of age and uses the device on a daily basis, then it's move on to a more active type of device, such as myoelectric or body power. Of course, there's different views on this, but that's the more updated version. And the other important aspect of this is that having the ability of having several prosthetic designs available. Research has found, it has been reported that when a child is exposed to more than one design, either mode of control, body power or myoelectric, or for different type of activities, activity-specific devices, they find that the prosthetic rehabilitation is improved. Now it's a problem because the cost of prosthetic devices is already high. So if you can even afford one, that's great. But affording 2 or 3 or 4, it could be a problem. So you probably understand why the development of this low-cost prosthetics is kind of important. It's a big deal. Other views also stress the importance of that. Children are not many adults, so they're very, very particular. They're very, very different. So things that work for adults is not going to necessarily work for children. Children, every time you get children a device, they put it to the test. They find ways to either break it or use it in ways that we don't really anticipate. Also, the development of motor skills, as I mentioned earlier, but also the focus in prosthetic rehabilitation, at least in some of the literature, is really focused. They indicate that it should focus in increases in range of motion and strength. So if you read between the lines, they seem to advocate for body power devices, which it makes sense because if you compare either the weight of a body power device versus a myoelectric, the body power device is typically going to be lighter. So some of the observations we can find, when you read the literature, is that the rejection and abandonment is quite high, so up to 58%. Now, it varies. It could be some research report 10% abandonment or rejection, but other literature is reporting about 58%. It could be higher or lower, but it is an issue. So what are the options out there? There's a lot of options. It's body-powered devices, myoelectric devices. Obviously, the cost is going to be a problem. That's not a secret. Now, there are institutions that provide prosthetic devices at no cost. There are non-profit organizations. But typically, there are minor details in which the minor issues that will stop the families from getting these devices. Let me give you a quick example. We have a child that I'm going to show you here in a little bit that needed a prosthetic device, $40,000. I think he had a chance to go to Shriners and get one for free. But believe it or not, the man could not take the day off. And sometimes because you cannot take actually a week off, to be honest with you, because the fitting procedures are very long, so the device fits well. So even things like that we don't anticipate are usually a problem. So how we make it easy for them to have access, or easy so we can have it in their hometown? How can we do things maybe at a distance instead of having the patients go to us, or maybe we can go to the patient? Those are the questions that are kind of very relevant. Feeding process is another obstacle for this, and also sometimes it's as simple as the lack of interest of the child. Believe it or not, sometimes you can give a child a device that's light, that's functional, but just simply they are not interested. They're not involved in the process. They don't care. And I'll show you some videos when a prosthetic device probably will make a difference. In partial hand amputees, the difference is negligible, but in fourth quarter amputees or shoulder disarticulation, it is a bigger deal. So before I talk about this, can you raise your hand and tell me if you're familiar with 3D printing, additive manufacturing? Okay, so you know what I'm talking about. So basically, is having the power of having a computer model. So imagine you draw something in your board or in your computer, a simple object, a simple figure, and then you take this figure, this idea, and manufacture it. So you get a real object, a three-dimensional object that you can touch and you can even use. So the power of this thing is basically that, is that you can put your imagination into reality. How does it do it? Well, it melts. It's basically like a glue gun. So there are thin layers of plastic that are melt one on top of each other until you get a three-dimensional object. So the only thing this machine is doing is following the coordinates X, Y, and Z of the digital file. It's a simple process. So the whole secret of this is not the machines, it's not the materials, the secret are the files. And I'm going to explain this a little bit more as we go along. So alternative options. I'm sure you have seen some of these 3D printed prosthetic devices in the media and so on. Let me make sure we understand each other. These prosthetic devices, I don't really believe, are a substitute for a prosthetic hook with the quality and functionality it has, or any other type of device. It's an option. It's yet another option. So it's not a substitute of any kind, because it's very hard to substitute something that really works really well. So the way how these devices work, so they're made out of plastic. The plastic is eco-friendly. It's like a thermoplastic. So it has a dial. The BOA dial is very well known. It's used in sports, it's used in prosthetics. And then also has the capsule at the bottom. So this, for example, this hand is for a partial hand amputee. Has no electronics in it, no electronics whatsoever, even though I'm dying to put EMG sensors in this. Don't get me wrong, that's my specialty in my PhD was that. But no, we're not doing that. Well, some of it at some point, but this is body powered. So the way how this works is the child is missing the digits. Then typically it fits into the socket, and when he flexes his wrist, the hand will close. So the function that this gives to the child is limited, but it does give some sort of function, and the cost is very low. It's about in materials it's about $50, which is inflated, to be honest with you, but about $50 or so. But does give the opportunity for a child to have something that looks like his hand and has some motion. He drives the hand, he flexes the hand. He's the one that chooses the colors, the design, and he's the one that uses it. And as I'm going to share with you, the rejection rate of these devices so far has been zero. We haven't fit a child that all the child we have fit, they are using it. Now, why? That's the question, why? I think it's because they're part of the process. They're involved in the process. They are involved in the design process. They get to choose it. Sometimes they don't like the color. Sometimes they don't like the way how it works, and we change it. Anyhow, so we have all the other type of devices as well for below elbow amputees. We have spent a lot of time making mechanisms that really facilitate the functionalities, such as the wrist mechanism. I'm going to share with you in a little bit. I have a video about this. The wrist mechanism was a big deal because it's very complicated to have a wrist mechanism that rotates without entanglements of the cables. However, there are mechanisms out there, but they are protected by a patent. So we felt the need to develop our own, and we open source it so everybody can use it. There is no harness on this device neither because it's very light. It doesn't need the harnessing on it. By the way, this is all the work I'm showing you here. You can have access to it. It's as simple as signing an agreement to make sure you're not selling it. But if you're using it for the patients, we'll send it to you. We'll send you all the files. We'll provide you with support and everything you probably need. So this is our objective here is implementation of this. Why? Because we see that it's something that may be helpful. It's another option. And especially people that have low resources, that they may not have access. I come from South America, so I know what needs is all about. I understand it, I feel it. I cannot forget it. Therefore, it's important to just give options. Here I'm going to show you a little bit, some slides about the impact. I'm at 14 minutes. So a little slide about impact. We team up with UNICEF, with UNICEF, in order to take our first designs. This is what you're seeing here is we call it Cyborg Beast. It's like Cyborg Beast 1. We name our designs. Who made the name? Who put the name to this design? It wasn't me. It was my son. Actually, he's 6 years of age now. So he put the name of the design. We have it pretty much all over the world, to be honest with you. So this is a sample from Nigeria. Then we also went to Johns Hopkins, gave a presentation about this. We're providing full support for the implementation. As you know, Johns Hopkins is really good at brain-activated devices, the top of the line devices. But when it comes down to something extremely simple, I don't think they're all that great. I don't think that. So that's why we're trying to help them out. The NIH also sharing our files in their website. So Aldo is the older design, so if you need the new one, you should contact us. And some examples of impacts. I'm not trying to brag here, but just, we make the cover of that, the CNN and BBC, and so just to give you an idea of that this thing is not just the Midwest, it's really around the world. TV shows and so on. Oh yeah, and also in 2014 we were selected as the top 5 inventions of that year, so that's very exciting. And all this is really, to be honest with you, is because it's open source. Now you may be wondering why not to patent this. Okay, yeah, I mean, we thought about that. I mean, I'm not when I lie to you. Of course we thought about that. But think about this: what happens when you patent protect something? Is that going to reach really the people that need it most? Okay, maybe, but how long is that going to take? I'm so impatient about this that we decided just not to patent it, share it, and thanks to that, it's having a lot of impact. Now we're not the only ones doing this. Now, I'm going to mention later, the VA hospitals, there are 5 that are fully implemented with machines and design and training. So this is coming strong. So it's going to be very hard for this not to span all over the place. It's exciting, it's scary at the same time, and it's change. So my recommendation is not to be so afraid of change, because this is, as you see, it's not that complicated. New, but not complicated. So now let's talk a little bit about research. This is the most important part. Before I give you some data and show you some publications, which I know that's what you're waiting for, let me show you how the hand works. So I'm going to share a video of the first patient that used one of the first hands we made. Very challenging. In this situation here, let me see if the video works or not. In this situation, see, the palm of the child is about less than 4 centimeters. I mean, very, 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 very short. The device that the child had was a device similar to the one below the pictures, a prosthetic hook. It's very similar to the device you would give to a below elbow amputee. And the reason for that is because the industry, so far, for this age, there is not really a practical solution for partial hands. They're very limited. So, when one of the reasons they went to our lab is because the child simply was not using, the harnessing and the whole arm because it was too heavy. I mean, it's obvious. She used this prosthesis. We didn't really know she was going to be able to activate it or not because the palm was so short. And the leverage system there, the mechanical advantage is very, very, very complicated there. It's not very efficient, really. But right now, actually, the video that I'm showing you here is the first minute she used the prosthesis. She hasn't practiced at all. There's no rehabilitation. I mean, we put it on. I just took my cell phone, took the video, and that's what you're seeing right now. I mean, this is not something I'm trying to stage or make it up. This is how it works. It's very intuitive for them. Now, what she asked us is something, as soon as she wanted purple, for some reason, we had one in pink for her, but she wanted purple. We did that. And then she asked us for nails because she wanted to paint her nails. Now, to be honest with you, those details, I think, are the secret to the success. Because if she wants nails and she wants to paint her nails, obviously, then she probably more likely to use it. So the daily usage is gonna go up if we do those things for her. Boys usually ask for lasers. Some people want some sort of weaponry in the prosthesis, and if it is safe, we usually do it. What we're not doing is just to amuse audience or amuse the family. No, we do it to increase the prosthetic usage, the daily usage. If we can go over, our average is low. Most children that use prosthesis, they report using it about 2 to 4 hours a day. I think that's a little bit low, so we're trying to increase that. How? Doing these silly things for us, very important for the children. This is a partial hand. Look, I know what you're thinking. When you look at this patient, so he lost the pinky and the ring finger, so there was damage in the ulnar nerve. Obviously, he cannot extend the digit and the middle finger because of the ulnar nerve damage. As you may be thinking, okay, that prosthesis is not going to work. It's not functional for him. He already has the pinch already. Why would you put something like that on his hand? It's true. In fact, that was our response. When the family asked us for a hand, our hand therapist looked at it and said, no, because it's going to be in the way. It's not going to be really very helpful. Well, we were terribly wrong. By the way, the person that literally made us make this device for the child was the dad. And I'm going to share with you real quick. So what happens is that, because I didn't understand why his dad would call me and email us and stop outside of our laboratory, at 6 in the morning. When I get there, it's about 6. He was already there waiting for us. The reason was because he had a lawnmower accident when he was 2 years of age. And the dad was driving the lawnmower, and the dad put the child on his lap. He fell, he ran over his hand. So, to be honest with you, this hand is not for the child, it's for the dad. Other thing is very important that we missed. Most of these devices, they are not even for the child, it's just for the families, and that's something for researchers like me, that I don't work with this type of population, as some of you do. I neglected, I didn't understand it. I'm just now understanding those issues. But a big deal. So let me show you exactly why we designed this hand. this, if you're a biomechanist, you will look at this hinge that I have on top of his wrist, and you'll say that's not gonna work. Well, because hinges are on the side for a reason, right? So we decided to put the hinge on top. But let me explain why. And actually, I'm going to show you the video instead of explaining, because it gets boring to talk about these things too much. So, let me see. Let me go back. Let me see if I can play it from here. Okay, so I want you to focus. I'm sure you play basketball or you know basketball. I want you to focus in the last portion of the follow-through. So when follow through of the wrist, the last flexion of the wrist, when the ball start and the fly fades, and the aerial fades. There. So I don't know if you noticed this or not, but what happened there is that, and this is, I'm showing you the pictures of the design of the device right there, those fingers. Well, what the purpose of this device was to allow the child to do complete follow-through, so he gets the backspin of the ball and have more successful rate in scoring in basketball. Okay, once again, may not be a big deal for many of us, but for him it's extremely big deal. He uses it just to play basketball. He doesn't use it for anything else because he has pinch already, so he can pinch things, but he uses it for sports. So just an example of the specificity of a few things. Now let's talk a little bit about research, because I'm running out of time here. So the first paper we published, by the way, the prosthetic hand, the open source that you see, we call it CyberBeast, it was the first one 3D printed prosthetic designs open source in the United States, and probably the second or third in the world. So what we did in this paper was to talk about this hand and how it works and all the fun, but something that I want to share with you is that we're using very simple assessment and using image-based editing computer softwares. We did the following. So basically, we had a hand therapist taking several anthropometric and range of motion measurements of the hand. So you can see those values right there. Then we took pictures. So we had these children taking pictures of the hand in a full extension, flexion, and then a superior view of the hands with a ruler. So what we did, we extract all the measurements and we compare the measurements that we extracted from the pictures versus the measurements that were done by the hand therapist. As you can see, the values, there were no significant difference and so on. Okay, at this point you're wondering, okay, this is not, okay, big deal. I mean, this is simple. Yes, it's very simple, but look at this. If we're able to, we validated it, we did validation analysis and so on. The relevance of this is that it would allow us to take grab an image, and the picture you see in your right is from a patient from Chile. So it gives us the possibility, just the possibility, of from a simple picture, not taking a scan, no, simple picture, low resolution picture you can take. I don't have my flip phone here, but I'll show it. With a simple flip phone that's very popular in Africa. You can take this picture and with a ruler, and we can get everything else from there. So really, we are able to, and this is why we did this very, very long time ago, and now this is the main way in how a non-profit organization is called Enable, that we help. We stepped aside from the non-profit organization because it's taking way too much time. So now we're fully dedicated to the research, but they use this design and the methodology. So by taking pictures, then you can get some measurements, and you can take the model of the prosthesis and superimpose those into the image. So this is all done in the computer software, in a computer modeling software. Import the picture as a plane, so you can see everything. Then superimpose the prosthesis on top of it, and you're going to get an idea of what the length, the size of the prosthesis is going to be. Now, there is the final details of the socket, and that's why now we're working with medical professionals, with CPOs, because they are the experts. They are the one that knows how to make this work. We are nobody. We can do nothing without their help, because they are the one that make this plastic hand a prosthesis. Not only CPOs, as you say, hand therapists and upper limb specialists and so on. The next paper I'm going to show you, we published, I think it was last year. Yeah, it was last year. We're trying to find what was, the benefits of using it beyond function. I'll show you some function in a second, but this is just beyond function. So circumference, strength, and things like that. Because if you think about it, what this hand is an exercise device for the affected limb. So you can gain some circumference, some cross-sectional area of the muscle. You can gain a bunch of different things. We took ultrasound pictures before and after and did a comprehensive analysis of muscle function. But the data I'm going to show you here, and I haven't had time to analyze all of it. So I'm going to show you here some of the data that we were able to publish. So here's some measurements of forearm circumference and skin folds and range of motion and so on. The data I'm showing you here, so you see all those lines. So the solid line is a non-affected hand, and the dotted line, the dashed line, is the affected hand. Now, why am I showing you the affected and the non-affected? Because we use the non-affected as control. Children grow, so you can't measure before and after, because they're going to grow. They're going to get their circumference is going to go up no matter what. They grow, so we have to use the other side as the control. Also, you can use other subjects, age-matched subjects as control, but we feel that this is better. We found significance in forearm circumference. So the affected hand, the circumference of the forearm was significantly more than the non-affected. It's the same child. After 6 months of using this hand for an average of 2 hours a day, 2 hours a day, every day. What type of activities? Actually, most of the 75% of them use it mostly for fun. Literally, that's what they put for fun. Very low percentage in school, very low percentage in sports, but mostly for fun. Changes in skin folds, we didn't find any significant. I don't know why we measure skin folds. I guess to be honest with you, our intention was to measure the cross-sectional area of the muscle by taking the skin fold and the circumference and do some linear regression equation there, but it didn't work out so well. So in any event, skin fold didn't change at all. But here's the big deal, what I think is range of motion increased. So a child using this hand for 6 months, it would increase their flexibility, range of motion, for extension and flexion. Now when we look at strength, if you look at the lines, it appears that it should be significant. It makes sense that it should be significant because the resist to open and close this, open it, there's no force. It's active. The extension is assisted by the elastic components of the hand that you're not able to, that are internal. But the flexion is active, so you're using force to flex it. So it would make sense that strength would increase. Well, it did not. It did not. Even though the numbers look it looked like it should, but if you look at the standard deviation and the sample size, we're talking about 5 children. That's all. 5. Believe me, in the world of prosthetics, 5 children is a lot. It's a lot. So I know most of you are looking at this and say, oh, this guy is underpowered. Yeah, I am, but this is the nature of this type of research. It's very difficult to find subjects, especially similar ages and so on. Okay, so let's move on to our next paper. So then we published this, I think, also last year. But more important than showing you that the development of a 3D printed prosthetic shoulder, which was actually this was there was the first 3D printed prosthetic shoulder like in the world, and why that's special is because it's designed to be printed in machines that are inexpensive, low-cost machines, desktop machines, those machines that you buy for $5,000. So we're not talking about the machines I have in my lab of $250,000. We're talking about $5,000 or less. So that's the big deal. But actually, that's not the big deal. The big deal is the rationale. So why would we engage in such an ambitious project? It's not because we were going to reach fame and be popular. To be honest with you, that's not I'm sure that's in the back of our hands. Some people in the back of our mind, but that's not the reason. So the rationale of the study was this: So this is a child that I was mentioning earlier. He's from Omaha, South Omaha. I don't believe the family have access to Shriners. Well, before explaining, I get very emotional about this. His name is Antonio, and I have a little kid that's also Antonio. My son is also named Antonio, so kind of hard to talk about it. But look, I'm gonna go ahead and show you the email I got from our local CPO. This email really expresses frustration of the CPO, of the professionals that are working with patients, and they see this on daily basis. This is not just us. This is so. If you read this, you understand that everybody wants to help, but sometimes it's very difficult to help. So, how can you possibly expect a mother to come up, and to be honest with this, a single mother, to be able to come up with an amount like that? And not just one time. This is just the first time. It's a little bit. I have difficulties understanding that. So what our response was this paper. So what we did, we started designing all digital. We designed this prosthesis. We do our biomechanical analysis virtually. So we didn't have to. We spend no money on this. This is all our time. That we did spend a lot of time, but that no money because it's digital. You do the stuff in the computer. You do the stress testing on the computer. You test everything first before you print it. And once everything is done, and I'm showing you the cost of this device. So in the publication, I have the breakdown of the cost, the weight, and the force of activation, and all the data you may want to hear. I can't explain it here because it's too long. But here you can see a picture of the entire design. So now this is our first try. His hand was too big. To be honest with you, he used this for about 2 weeks or so, and then he asked us for a new one. So we developed a new one, and then that one broke. So we're working on our third trial. So typically, in a period of 1 year, he has had 2 shoulders prostheses, which is not a big deal for us because the cost is low. It's $200. So I got a grant, a small grant. I haven't got any big grant. I got a small grant from NASA for like the mini grant, for $20,000. So I have a lot of money to give him as many shoulders as he wants, really. But that's the beauty of this, really. That's kind of the beauty of that. As many of you know, the American Orthotic and Prosthetic Association is celebrating 100 years. So we submitted an abstract looking at the technical and clinical considerations of development of this type of devices. Fortunately, it was selected. Well, it's being selected as one of the presidential papers. So we wrote the paper already. We submitted it, and it's just what I'm gonna give you here is some. I know you can read this stuff. I understand, but just to give you, this is more for me to remind me of what I'm gonna talk about. So we're gonna talk about first about the few steps. So the steps of the remote fitting procedures in detail. Then we're going to talk also about the specification and materials that you should be using for this type of devices, and then the post-processing and assembly process of these devices. So this is a resource for the clinicians to have and to go into detail about implementation. We'll talk about the technical, medical considerations, and resources. We give a bunch of resources that are open source software that you don't have to pay anything. The implementation for this, folks, is very not costly at all. You can do a lot of this with very little money. So I'm an assistant professor, and I haven't got any NIH grant, I don't have any big grant. All this work I've done is with very little money from the states, from companies, from here and there. So the implementation is very low. Here I'm showing you some videos of our devices. The second video you can see there is the wrist mechanism. We did that wrist mechanism because she asked us to. So this whole research is driven by the patient, by this research subject. They ask us, we do it. In the paper, and I'm showing you this because this is part of the review paper that hopefully is going to be published soon. So I'm giving you information that's not out there yet. We have developed devices with sensors on them, with a bunch of different sensors like you have in your cell phone, to identify the functions, to identify the usage. Okay, the children are using the prosthetics for what? Riding the bike, how much time they use it for manipulation, stabilization. We want to get details to improve the design. The other device that you're going to see in the review also is this. Let me show you again. So you see the video, it's in your left, in your right. That video is a scanning device that we developed, and we're willing to share it with people. I know this is not very popular for administration at the university because it should have been patented, but we strongly think that if we don't share things, they're going to get lost somewhere. It's going to take forever to go to people. That device right there is replacing a device that it costs about $50,000. This device is about $250. It's made out of plastic, and it gives the software. We developed the software. The software is ours. It's open source, and also you can put your cell phone. So you take several pictures of the affected limb, and you get an image that you can work with. So this is how we're doing the prosthesis in Chile. We have a machine like that in Chile. They get their scan. They send an email with the file. We do all our work here. We develop the prosthesis, send it back to Chile. So it is possible. It's possible. We can do it with pictures too. If it's $250 is too much, we also have pictures. So there's 2 papers that I want to mention here, but that we just submitted recently. Actually, this year, a couple months ago. The first paper we did it with the folks in Chile. So all the work we do is research-based. Nowadays we don't do work if it's not evidence-based, if it's not research-based. So with the folks in Chile, we developed the hand. So I'm going to show you some results. This result of this study was negative in terms of the shows that the hand didn't work at all. And it's extremely exciting, because and then you wonder why it didn't work. Well, I added, if you see the column in table one, some of them had the ability to pinch. So if you have the ability to pinch already, why would you use this? Those are some of the challenges of working with scientists in other part of the world, because you can't really see how the patients are being recruited and so on. In any event, the results of this study were negative. The children perceived that the hand wasn't really helping, even though if you look at the children with no ability to pinch, and you look at the functionality scale they use, you can see some improvements. But in general, the paper showed that it didn't work. So and then we felt that we needed to do it again. So with the same team of scientists, repeated the study with 11 subjects now. The first one you saw was 5. We did only children without the ability to pinch, and this is the box and block test. And I'm sorry for the small numbers, but we did the box and block, so you can see the differences, 6 versus 13. So after 1 to 6 months, they increase the functionality. The conclusions, and I have 5 minutes, I think I can do it. The development of testing and implementation of 3D printed prosthesis is an early stage. It's extremely important that this ability of having open source files that you can access, that I can access, and you can mess around with it and modify it is extremely important, because that's how we make the progress. That's how we improve things. Also, that's very important is that the collaboration among CPOs, among hand therapists, computer engineers, biomechanists, and is extremely important for the success of this. So, believe it or not, being having folks from different fields is a plus, and I expect this movement on this type of designs to improve significantly in about a year or 2. And as I mentioned earlier, there is 5 centers of the VA that are doing this already. They're trying to reach full implementation. Now, the other point I want to make, 2 weeks ago I came back from China, actually last week, and I can see the sense of urgency. So the Chinese government is really, really, really aggressive in trying to implement this. Their prosthetics are not made in China, believe it or not. Their prosthetics are made in Germany, Autobahn. That's the majority of prosthetics they get. Kind of expensive. So the Chinese government that funds 100% all the rehabilitation centers is very aggressive in trying to lower the cost. So that's one of the reasons I went there and spent about 7 to 10 days. That's why I haven't slept for like probably 48 hours because my sleep is all messed up. Future areas of research. I'm going to go fairly fast on this. Absolutely, we're going to do lower limb devices for sure. Now, the durability of the prosthesis is a concern. Now we're working on that, but I do believe that lower limb exoskeletons or prosthesis and so on is a possibility. Here's a device that we are working actually for one of the patients in China that has a spinal cord injury. This device is able to passively extend, actually to actively extend and passively flex. It seems to be the problem with the hand spasticity and so on. And also we're looking at the influence of this type of devices in brain activity. This is something that is something that we're doing right now as we speak. What happens to the connection, to the representation in the brain of the hand and arms of children that never had it, of children that were born without a hand or an arm? Are those representations there? If they're there, what is the influence of a prosthetic device? What would a prosthetic device do to them, to those areas of the brain? Well, I have no idea what they do, but we're trying to get an idea. Now, this instrumentation we're using is somehow limited. FNIRS. It's very hard to take a child and make him stand still for an MRI scan. So we're trying to start to do things, with FNIRS first and see what happens. And we may move to EEG. We don't know yet. It's all depending on how well the children behave and are able to sit down there for us and doing forward reaching. Anatomical modeling is one of them, and it's another way of implementing this research. And I'm running out of time, but we also are doing, because people ask us, not because we want to be honest with you, because this is a little more expensive. Rehabilitation centers that we work with are asking us to do anatomical modeling, and we can't say no to people, so we are doing those things. So here you have a few examples of anatomical models. We partner with Children's Hospital, and we're working in several anatomical models. We have done about 13 or 14. And with this, I'm going to open it for questions. And first of all, I want to thank you for listening and being up so early. Thank you. If you can pass this around. I'm going to pass some models around. This is an anatomical model. And
question about your lower extremities.
Yes.
Because obviously durability is a big issue when you're dealing with the prosthetics. Like, what kind of materials are you looking for then?
Right now we're looking at nylon 680. That's a material that supposedly is hard to print, but a material that supposedly is going to give us the strength and a little bit of flexibility we need. To be honest with you, the industry right now is working very hard in new materials. So every week there's new materials, new development that have different strength and different applications. But right now, to answer your question, nylon 680 is the one we're looking at. Yes.
Well, thank you for a wonderful talk. I have 3 children, and one of the biggest problems we have is it seems like every few months we have to buy new shoes for my boys. So the question is, how do you design prosthetics which are, reconciled with the tremendous growth that children go through? And what is the half-life of the devices? How often do you feel like you need to get a new one?
Okay, the half-life of the device is gender dependent and age dependent. So boys last no more than 2 months. We have found that for somehow something happened with the device that malfunctioned within 2 months for the boys. For the girls, is about 6 months actually. Now I'm talking about the newer devices, because the first devices, they wouldn't last a week. They were printed wrongly, they were laminated, and then there was a disaster, to be honest with you. But we have learned. So the devices you can see, the devices going around, that one for a female will last 6 months, and for a boy about 2 months. The more challenging ages is 8 to 12, in which they do really upsetting things to the prosthetic devices. We have surveyed this, and we have asked the families, how did the device broke? Because we want to know that. I mean, we really want to know that. And the number one reason that the device is broken, that's reported by the families, is fights among children, among siblings. They fight. I'll show you this. In Omaha also there was a family that was visually impaired, and they asked us. She was expecting a baby, so they asked us to see if we can get a volumetric file, like an ultrasound file, which is very hard to do, into an object so they can feel the baby's face. I'm gonna go ahead and pass this around. I'm sorry, introduce that. You should see that. Do you have a question? Yep. That's interesting. That's very interesting.
Have you had any kind of like group of, say, teenagers who are amputees who have tried different prostheses to kind of look at what works and what doesn't work?
Yeah, the teenagers in Chile, in South America, we did that, and with them it's a little bit difficult, to be honest with you. They don't want something flashy. The kids that are 8 and under, they want something the flashiest thing as possible. Bright colors, lasers, and all voice-activated things. I mean, they love all that stuff. But when they get to that age of 15 and 16 and 17, we have found that our devices usually are rejected, the ones that are very flashy. So what they really want is either a device that kind of doesn't bring too much attention. And that's something we're also learning. We don't have a developmental psychologist in our team, but it's an important factor. So we have made a lot of mistakes. Yes?
So in Chile or in any other country where you're developing these, do you have to train people there to basically put together the processes after they're printed?
Oh, right. No, that's important. That's very important. So the non-profit organization we helped develop a long time ago, they work directly with the families. And it took me about a month to figure it out that that's probably not the best way to do it. So now what we do is, in Chile, we're the first ones to kind of implement the new model where we work directly with the healthcare professionals. So the CPO, the hand therapists, the surgeon are there. We usually go there, we show how the device works, we do workshops, we do seminars, and then we share the files. But initially, before sharing anything, we do a pilot trial with the children to see if they are going to set the device or not, and how it works, and so on. So the team gets familiar with it, which it takes them nothing, about a few days. They know this is still better than any of us. So then, after they're familiarized with the project, then we jump to the implementation phase, which requires them to manufacture their own devices. So they get their equipment. So in Chile, I helped finance that with the government. We wrote some grants. We got the funding down there, and they're very independent now, so they can print their own devices by themselves. They don't really need us that much. For new devices, they do. So that's kind of the way how it works. It's a process. It takes about 4 to 6 months for them to reach full independence and do the things they want to do. All the needs of the patient in different parts of the world are completely different. Completely different.
I hope you'd mention also that we're going to be doing a workshop here at some point in the future, trying to set things up, but we might need volunteers. We're going to bring some of the local children, probably off-site, just to see how we can help them and collaborate with you.
So yeah, I did mention this. So we have been working with Children in Mercy, and especially with Anne team for a while now. And we always meet in conferences, we talk, and we have a good experience. We have worked with some of her patients, and we have had good experiences. So yeah, we will be doing a workshop pretty soon. And anything you need, let me know. We'll keep you informed. We'll let you know when is this going to happen, and we'll give you all the details. Thank you for mentioning that.
The questions, I want to thank again Dr. Zuniga. I hope this really triggered some thoughts about how care of your own patients and how this technology is really rapidly advancing and really changing the field. So thank you, Dr. Zuniga, for visiting with us